Hello and welcome. Today I shall be discussing on the topic sequences. Definition. A sequence is a function whose domain is a set of natural numbers and the range the set of real numbers. So a function f, domain is capital N, the set of natural numbers, and the range is R, the set of all real numbers. Before now, we define a real valued function as a function f whose domain is R and range is also R, set of all real numbers. Now, what's the main difference between these two definitions? Of course, is the domains. So for a real valued function, the domain is set of all real numbers. That is to say that any number that is real can come into the domain. While if a function becomes a sequence, only natural numbers are allowed into the domain. What are natural numbers? Numbers that are counting numbers starting from 1, 2, 3, and so on and so forth. Of course, there are some persons who start the natural numbers from 0. But in this video and all subsequent videos, I shall be consistent by starting natural numbers from 1. So let me give a quick illustration, on the difference between a function that is a sequence and a function that is just a real valid function. If I have the function, say, 2n plus 1, 2n plus 1 also. Now let's see what happens. If this is a real valid function, okay, so I can just write here f of n is equal to 2n plus 1. Now, in the domain of this function, I can plug in any value. For example, I can say when n is equal to half, what happens? I have f of half equal to 2 times half plus 1. That's equal to 1 plus 1 equal to 2. For a real value function f that I've defined here, to find, I've checked out the value of one of the terms by plugging in the number half into the function. But if this function is a sequence like it is here, 2n plus 1, I cannot plug in 1 over 2 into this function because 1 over 2 is not a natural number. 1 over 2 is a real number, but not a natural number. Because natural numbers do not include fractions. So if this 2n plus 1, this function is a sequence, I want to now write an equal to 2n plus 1. So that if n is equal to 1, I can get the first term of my sequence. And that corresponds to a subscript 1 because n is 1. That's equal to 2 into 1 plus 1. That gives us 2 plus 1 equal to 3. So for this sequence an equal to 2n plus 1, the first term of the sequence, which corresponds to the term gotten when n is equal to 1, is equal to 3. To get the second term of this sequence, I have n equal to 2, so that becomes a2 equal 2 into 2 plus 1 is equal to 4 plus 1 equal to 5. So the second term of my sequence here is 5. While for my real value function here, I can plug in my values for n arbitrarily, anyhow, in no particular order. But for a sequence, when you plug in 1, the next one you must plug in is 2, the next one you must plug in is 3, just to get the terms of the sequence, in the order. Let's get 2 more terms of the sequence. So when n is equal to 3, I'll get a3, that's the third term of the sequence, as 2 into 3 plus 1, that gives me 6 plus 1 equal to 7. And when n is equal to 4, I have a4 equal to 2 into 4 plus 1, that is 8 plus 1 equal to 9. Of course, I can go on and on. So, an equal to 2n plus 1 have the following terms, or has the following terms. First term there is 3, which corresponds to when a is equal to 1. My second term is 5, which corresponds to when a is equal to 2. My third term is 7, which corresponds to n equal to 3. My fourth term is 9, which corresponds to n equal to 4. And of course, this can go on and on forever. So, the terms of this sequence have been generated from this function. And we now call this function now, for the case of the sequence, we call it the nth term. This is called the nth term of the sequence. Why is it called the nth term? It's called the nth term because with this term, we can get any term of our sequence. We've gotten term 1, term 2, term 3, term 4. We have term 5. We can get term 6. We can get term 8 of the sequence. For example, the 8th term of the sequence would correspond to where n is equal to 8. And that will be A8, the 8th term, equal to 2. We now put 8 for n, 8 plus 1. And that will be 16 plus 1 equal to 17. So the 8th term of the sequence is 17. I hope you get the clear difference between a function that is a sequence and a function that is just a real valued function. For the real valued function here in the domain is R. So here we can plug in just any number that comes to your mind, except complex numbers. We can plug them in here. While when that function becomes a sequence, we are restricted. The domain now becomes only the set of natural numbers, which starts from 1. And in some other cases, it starts from 0. Whichever one you're using, you have to be consistent. So we'll be using n starting from 1 going forward. So another function I can define here, I can define, say, 1 over n. So if 1 over n now, if I claim that 1 over n is a sequence, it would mean that my n here, the n here, must only come from capital N, the set of natural numbers. So if I put this restriction, that makes this function a sequence. So I can write here xn as my sequence. So x and subscript n. So that the first term of this sequence can be gotten when n is equal to 1. And that becomes x1. 1 over 1 equal to 1. So the first term of my sequence, 1 over n, is x1, which is equal to 1. The second term is gotten when n is equal to 2. So x2 is equal to 1 over 2, which is equal to 1 over 2. I can get the third term of my sequence when n is equal to 3, as x3 equal to 1 over 3. I can get the fourth term, n equal to 4, and that will be x4 equal to 1 over 4. I just put in the corresponding value of n into the function or into the sequence. What do you observe? The numbers I put into this function are all natural numbers. 1, 2, 3, 4. I can now put 5, I can put 6, I can put 7. What I cannot put here are fractions like rational numbers. I cannot put 1 over 2. I cannot put 3 over 8. I cannot put 10 over 11 because those numbers are not natural numbers. But for a real value function, I can put those numbers I've just mentioned. So I can write out the terms of this sequence now. I can now write my sequence xn, which normally we put between these two parentheses, is equal to, the first term is 1, the second term is 1 over 2, the third term is 1 over 3, the fourth term is 1 over 4. And of course, the sequence can go on, we can keep listing the terms, forever and ever. Now, a sequence, we now know what a sequence is. So we've gotten two sequences here. The first one is sequence an equal to 2n plus 1, where 2n plus 1 is the nth term. Here we have the sequence xn equal to 1 over n, where 1 over n is also the nth term. Now a sequence is either finite or infinite. Let's go back to the sequence xn. Xn has 4 terms. 1, 2, 3, 4. 1, 1 over 2, 1 over 3, 1 over 4. Let's assume for a minute or for a second that these are the only terms of this sequence. So a more appropriate way of writing this would have written this as xn is a sequence n starting from 1, from the first term from 1 to 4. So this would mean that the terms of the sequence should be the first term, the second term, the third term, and the fourth term, which corresponds to 1, 1 over 2, 1 over 3, 1 over 4. If these are the only terms of this sequence, then this sequence is said to be finite. This sequence is said to be finite. Finite in the sense that we can tell how many terms are in this sequence. In this case, we can tell that this sequence xn, where n goes from 1 to 4, has 1, 2, 3, 4 terms. We can tell that the sequence has exactly 4 terms. That makes the sequence a finite sequence. On the other hand, if I have my sequence, let's say the sequence an here, n going from 1 to infinity. Now n is not going from 1 to 4 anymore, or 1 to 8, or 1 to 10. It's going from 1 to infinity. And infinity is not a number we can get to. So this would mean that the terms of this sequence, should be infinite. So here we have 3, we have 5, we have 7, we have 9. The next term would be 11. The next term will be 13. But since the sequence is an infinite sequence, we cannot keep listing, forever. We now put 3 dots, 1, 2, 3. Now the presence of these 3 dots tells us, that the terms of the sequence go on indefinitely. This makes this sequence an infinite sequence. And we can know that the sequence is infinite already from the way the sequence is defined. That an is a sequence where n goes from 1 to infinity. This tells us already that this sequence we're dealing with is an infinite sequence. So a sequence is either finite or infinite. However, in the course of this video or this lecture, we shall be dealing mostly with infinite sequences. We now look at what we call bounded sequences. But before then, we must know when a sequence is bounded above. So a sequence n goes from 1 to infinity, that makes a sequence an infinite sequence, is said to be bounded above if there exists, condition, if there exists a real number, say k, so k is any real number, which is larger than all the terms of the sequence. Mathematically, n from 1 to infinity, that's a sequence, is bounded above if there exists, this symbol is a mathematical symbol for there exists, if there exists a real number k, so k is an element of R, the set of all real numbers, such that that real number k is bigger than or equal to an. An here means all the terms of the sequence. We can also write this as that this sequence an is said to be bounded above if the terms of the sequence an are all less than or equal to our real number here k. Of course, an is a sequence, therefore n must only come from the set of natural numbers. Let me explain this definition with a concrete example. Or let's take that definitions first, then examples will follow. Bounded below. A sequence n from 1 to infinity, again infinite sequence, is said to be bounded below if, condition again, if there exists a real number, say m this time, because the real number for bounded above might not be the same for the one bounded below. In fact, they are different. Say m, which is smaller than all the terms of the sequence. Mathematically, we write that the sequence n from 1 to infinity, is bounded below if, again, there exists a real number m such that that real number m is smaller than or equal to all the terms in my sequence, or if all the terms in the sequence are bigger than or equal to that my real number m. Of course, since it's a sequence, I say for all. This means for all, small n in capital N. So this simply means that I am taking my numbers only from the set of natural numbers. That makes this a sequence. Now, what is a bounded sequence? A sequence is said to be bounded if it is bounded above as well as bounded below. Hence, a sequence an is bounded if there exist two real numbers, m and k, such that an, the terms of the sequence are all less than or equal to k. Now, this part defines bounded above, and this other part here, small m, less than or equal to all the terms of the sequence. The second part here defines bounded below. So what do you observe here? We observe that to define boundedness of a sequence, we must define bounded above and bounded below. So what this is simply saying is that a sequence will be said to be bounded if that sequence is bounded above and also bounded from below. So here the sequence is sandwiched between two bounds, where the first bound, the bound on the right hand side, is the upper bound, or what they call bounded above, and the bound on the left hand side is the lower bound, or we say it is bounded below by m and bounded above by k. And of course, for all terms, for all n coming from the capitals, the set of what? Natural numbers. It is time to give concrete examples and explain in detail what we mean by bounded above, bounded below, and of course, boundedness of a sequence. Example 1. We have a sequence minus n all squared, or minus n squared rather, n from 1 to infinity, an infinite sequence. So we want to investigate if the sequence is bounded below, or bounded above, or bounded. So I can use xn is my sequence. N goes from 1 to infinity, and that sequence, the nth term there is what? Minus n squared. So what are the terms of this sequence? What are the terms of this sequence? Let us get a few of them. To get the first term of this sequence, that will be where n is equal to 1, our first natural number. So when we put in 1 here, we get minus 1 all squared. That gives us minus 1. So the second term will be when n is equal to 2. So that is minus 2 all squared. That will be minus 4. The third term of the sequence will be where n is equal to 3. So minus 3 squared. That is minus 9. Let's take one more term. When n is equal to 4, negative 4 all squared, and that is minus what? 16. So since this sequence is an infinite sequence, we could take the fifth term, we can take the sixth term, and so on and so forth. So a few terms. We have the first term as negative 1, second term as negative 4, third term as negative 9, fourth term as negative 16. Since our sequence is infinite, I put in 3 dots, 1, 2, 3, to tell us that there are more terms, of the sequence. As a matter of fact, there are infinitely many more terms for the sequence. It's time to investigate the boundedness or otherwise of this sequence. And to help us visualize what is happening, let's do this. So I have my real number line here. So from minus infinity to minus infinity rather this way to plus infinity. Okay. Now I want to arrange the terms of this sequence on the number line in the order, in order of their sizes. I have negative 1. So negative 1 is somewhere here. I have negative 4. Now negative 4 and negative 1, which one is bigger? Sometimes we are confused. Let me show you how to know which one is bigger. Now we have 4 and 1, right? 4 and 1. So let's knock off the negative sign and check which one is bigger. Now 4 is naturally bigger than what? 1. But when you multiply both sides by minus 1, you now have minus 4 here, and here becomes minus 1. And once you multiply an inequality by a negative sign, the order of inequality will change. So from greater than becomes what? Less than. So 4 is greater than 1, but in the negative sense, minus 4 is less than minus 1. So that means that minus 4 will be to the left of minus 1 on the number line. So minus 4 will be somewhere here. Then minus 9 will be somewhere here. And of course, minus 16 will be here. And the terms go on and on. So this is my first term x1, my second term x2, my third term x3, my fourth term x4. And of course, the terms keep going, downwards or leftwards, if you like. Boundedness. Now, I will claim now that this sequence is bounded above. I want to say that this sequence is bounded above, and I will say it's bounded above by minus 1. Why do I say that? So let us go back quickly to the definition of a bounded above sequence. Now we had said that a sequence is bounded above if there exists a real number k that is bigger than or equal to all the terms of the sequence, or if all the terms of the sequence are less than or equal to a particular real number, what? K. So let us see if that happens, if such a real number exists in our sequence. Let's look at the number minus 4. So there's a second term equal to minus 4. So if I claim that minus 4 is the upper bound for this sequence, that would mean that minus 4 is bigger than all the terms of this sequence. Let us see. I'm at minus 4. Minus 4 is bigger than minus 9. That is correct. Minus 4 is bigger than minus 16 rather. That is correct. Minus 4 will be bigger than the next term. Minus 4 will be bigger than the term that follows that next term. But minus 1 here is still an element or is still a term of our sequence xn. But minus 4 is not greater than minus 1. That tells us that minus 4 is not or cannot be our upper bound. Or that tells us that this sequence cannot be bounded above by minus 4. Because there is a term of this sequence that is bigger than minus 4, namely minus 1. So if minus 4 should be the upper bound of this sequence, it will mean that no other term of this sequence should be bigger than minus 4. So let's shift over to minus 1 and see if minus 1 satisfies that property. So minus 1 is a real number. Remember, k must be a real number. So minus 1 is a real number, is from R. Now, is minus 1 bigger than or equal to all the terms of this sequence? Let us check. Minus 1 is bigger than minus 4. Minus 1 is bigger than minus 9. Minus 1 is bigger than minus 16. And it's now obvious that minus 1 here will be bigger than all the terms of this sequence. So minus 1 is greater than all the terms of the sequence. But in particular, minus 1 is equal to minus 1 itself. So minus 1 is greater than or equal to an, where an means all the terms of the sequence where n is in capital N. So this simply means that this sequence above is bounded by minus 1. What this simply means is that there is no other element or there is no other term of this sequence, of the sequence, that is bigger than minus 1. In that case, we now say that minus 1 here is the upper bound of the sequence. We see that the sequence is bounded above by minus 1. However, this sequence is not bounded below. Why do we say so? Because there is no such n that is less than or equal to all the terms of our sequence. Since the sequence, the terms keep going, this is minus 16, this is the next term, this is the next term, and they keep going on, and we do not even know which of these terms is the smallest of all terms. The next question we want to ask ourselves is this: that minus 1 is the upper bound of the sequence. Does it mean that minus 1 is the only upper bound? The answer is clearly no. Let us check. After minus 1, there are so many, real numbers to the right of minus 1. There's 0, there is 1, there is 2, there is 3, there is 4, too many of them. In fact, these are just integers. Between minus 1 and 0, there are already infinitely many real numbers instead. Between them, between minus 1 and 0, there are so many real numbers. Between 1 and 2, there are too many of them. Between 2 and 3, there are so many. So let us just use the cases where we have our positive integers to investigate. 0 is to the right of this minus 1. So can 0 also be called an upper bound? Let us see. If 0 satisfies the property of upper bound. 0 is greater than minus 1. 0 is greater than minus 4. 0 is greater than minus 9. And of course, 0 is greater than all the terms of our sequence. Since 0 is greater than all the terms of our sequence, that qualifies 0 to be called an upper bound. Let us take 2. Is 2 greater than all the terms of the sequence? The answer is yes. Since 2 is greater than minus 1, 2 is greater than minus 4, and of course, 2 is greater than all the terms of our sequence an. Even if we pick, fractions, let us say, okay, between 2 and 1, there is 1.5. So let us take here, in between them, there is 1.5. Is 1.5 also an upper bound? The answer is yes, because 1.5 is greater than, once again, greater than all the terms of my sequence. So this tells us that though minus 1 is an upper bound for the sequence xn equal to minus n squared, there are infinitely many upper bounds. And this is a property that upper bounds will enjoy. That once there exists an upper bound for a particular set or a particular sequence, there exist infinitely many more upper bounds. I hope it's clear. So we are saying here that this sequence is bounded from above by what? Minus 1. So we'll now write that the upper bound, so upper bound for our sequence xn is equal to negative 1. This simply means that minus 1 is that term that is bigger than or equal to every other term of a sequence. Hope it's clear. Now, since this sequence xn is bounded above and not bounded below, the sequence xn is said to be not bounded. It's not bounded. Because for a sequence to be bounded, it has to be bounded above and bounded below. So in this case, our sequence is bounded only above, but not below. Hence, the sequence is not bounded. Here we have another sequence. 2 raised to the power n. N goes from 1 to infinity. Again, an infinite sequence. So I want to call this sequence my an, n from 1 to infinity. And an is simply what? 2 raised to the power n, which is n from 1 to infinity. So we always start by getting a few terms of a sequence. That to tell us the direction. So the first term is when n is equal to 1. and that is 2 raised to the power 1, which is 2. So the first term of my sequence, A1, is 2. Second term is when n is equal to 2, so that is 2 squared equal to 4. Second term of my sequence is the number 4. The third term is when n is equal to 3, so 2 raised to the power 3 is 8. So the third term of my sequence is 8. Let us take one more term. The fourth term, 2 raised to the power 4, is equal to 16. The fourth term is 16. Since the sequence is infinite, so the terms go on forever. Good. So my sequence is given with a few terms, 2, 4, 8, and 6. These terms are enough to tell if the sequence is bounded above or bounded below. Let me use a number line scenario again to explain the boundedness of this sequence. So I have my number line once again. Here is my negative, or positive rather, positive r if you like, or infinity, no problem, and negative infinity or negative r. Now 2 somewhere here, so that corresponds to the first term. 4 is to the right of 2 because it's bigger than 2, so this is 4. 8, 16, of course, the terms go on forever. So 2 here corresponds to A1, my first term. This is A2, my second term. A3, the third term. And of course, A4, the fourth term. And the terms go on forever. Is this enough to tell if the sequence is bounded above or bounded below? We check our conditions for bounded above and bounded below. Let us try to see if the sequence is bounded above. Let's check. If I claim that 8 is an upper bound for my sequence, what it would mean is that 8 is bigger than every other term of this sequence. Let us see. 4 is a member of this sequence and 8 is bigger than 4. Satisfied. 2 is a member of this sequence and 8 is bigger than 2. Satisfied. But 16 is a member of this sequence and 8 is not bigger than 16. So 8 cannot be an upper bound. If I pick 16 as my upper bound, that means that 16 is bigger than every other term of this sequence. 16 is bigger than 8, yes. Bigger than 4, yes. Bigger than 2. But there are terms after 16 that are bigger than 16. So 16 cannot be an upper bound. Because these terms keep increasing towards plus infinity forever, it simply means that this sequence has no upper bound. Because whatever number I pick, or whatever term of the sequence I pick in front, if I pick a term here and call this term an upper bound, there is always a term after it that is bigger than that term. And if I pick the term after it as my upper bound, there's always another term after it that is bigger than this. So this, behavior, will continue indefinitely. So that makes this sequence not to be bounded from above. Let us check if it's bounded from below. If again I say that 8 is a lower bound, or if I say that the sequence is bounded from below by the number 8, what it will mean is that 8 should be smaller than or equal to all the terms of my sequence. Let us see. 8 is smaller than 16. Very good. But 8 is not smaller than 4. So 8 cannot be the lower bound. Let us pick 4. 4 is smaller than 8. Good. Smaller than 16. Good. And every other term to the right of 16. But 4 is not smaller than 2. So 4 cannot be my lower bound. I now go to 2. 2 is less than 4. Very good. 2 is less than 8. Good. 2 is less than 16. And 2 will be less than every other term on this sequence, since they all lie to the right hand side of 16. So 2 is less than every term of the sequence, except itself, because 2 is equal to 2. So 2 is less than or equal to all the terms of this sequence. That simply means that 2 must be our candidate for lower bound, because 2 is less than every other term of the sequence, and of course 2 is equal to itself. So we now say that this sequence here, an equal to 2 raised to the power n, is bounded below by what? By 2, and not bounded above. I've explained already why it's not bounded above. The next question is this: that this sequence is bounded by 2, does it mean bounded below rather by 2? Does that mean that 2 is the only lower bound? The answer is no, because to the left of 2 we have infinitely many real numbers. For example, we have a 1 here, we have a 0, we have negative 5, negative, there are so many. Even between 1 and 2 here, there are just too many real numbers that we cannot count. Let us see. Let us pick this one 1 for clarity and for simplicity also. Can 1 be called a lower bound for this sequence? Let us see. For 1 to be called a lower bound for the sequence, it will mean that 1 must be smaller than or equal to all the terms of the sequence. The terms of the sequence begin from 2. So is 1 less than 2? Yes. Is 1 less than 4? Yes. Is 1 less than 8? Yes. Is 1 less than 16? Yes. And indeed 1 will be less than every other term of the sequence. So since 1 is strictly less than all the terms of the sequence, that qualifies 1 to be called a lower bound. And of course, between 1 and, let us look at how about 0. 0 is less than 2, is less than 4, less than 8, and is less than every term of the sequence indeed. So 0 is also a lower bound for the sequence. And of course, that goes on and on. If you pick between 0 and 1, there's 0.5. 0.5 is less than 2, is less than 4, less than 8, less than 16, and every other term to the right. So 0.5 is also a lower bound for the sequence an equal to 2 raised to the power n. So, since the sequence is bounded below by 2 and is not bounded above by any real number, this sequence an equal to 2 raised to the power n is said not to be bounded. So it's not a bounded sequence. For the sequence to be bounded, it must have a lower bound and also as well as what? An upper bound. So in this case, we only have a lower bound, which is what? 2. Of course, there are many more lower bounds. We'll pick 2. Understand that it will not be wrong if you pick any other lower bound apart from 2. But very soon you'll see why 2 is always, one of the best choices of the lower bounds to pick very soon. Our next example, I want to check also if this sequence n over n plus 1, n from 1 to infinity, is bounded above or bounded below or bounded. So we take the first few terms of our sequence like we used to do. So for n equal to 1, we take the first term, that is 1 over 2 plus 1, that is 1 over 3. 1 plus 1, 1 over 2. So the first term of our sequence is half. The second term of the sequence is when n is 2, so 1 over 2 plus 1, 1 over 3, 2 rather, n is 2. So that is 2 over 3. When n is 3, we have here 3 over 3 plus 1, that is 3 by 4. So we have here 3 over 4 is the next term. And let us take one more term. When n is equal to 4, we have 4 over 4 plus 1 equal to 4 over 5. So we have 4 over 5. And of course, our sequence goes on indefinitely, since the sequence is an infinite sequence. So we have taken from n equal to 5, we can take n equal to 6, and n equal to whatever it is. It is time now to investigate if this sequence has an upper bound, if the sequence has a lower bound, and if the sequence is bounded. So to make things life easier for us, like I've always done, I'll place these terms on a number line so I can see which numbers are greater. So this is my plus r, or plus infinity if you want, and minus infinity. So the first term there is half. So I'd like to write the decimal equivalent of these numbers, since it will help us to know which number is to the left and which one is to the right of which number. Now 1 over 2, if you punch a calculator, is the same thing as 0.5. 2 over 3 is the same thing as 0.67. 3 over 4 is the same thing as 0.75. 4 over 5 is the same thing as 0.8. Okay, so it's obvious now. It's now clearer in decimal form which is greater. For example, now 0.67 is bigger than 0.5, clear. 0.75 is bigger than 0.67, clear. 0.8 is bigger than 0.75, clear. Of course, the next term will be 5 over 6, and so on and so forth. So 1 over 2. So we place 1 over 2 somewhere here. Call here 1 over 2. The next term is 2 over 3. Should 2 over 3 be to the right of 2 or left of 2? Let us check the decimal. 0.67 is bigger than 0.5. So 2 over 3 is bigger than half. So to be to the right. So 2 over 3 should be somewhere here to the right of half. 3 over 4 is 0.75. Is bigger than this one. Should be to the right. 3 over 4. And 4 over 5 will be to the right, 4 over 5. Since 0.8 is bigger than 0.75. So, this is, say, A1, our first term, A2, second term, A3, third term, A4, our fourth term, and the terms go on and on. We'll now check if the sequence has an upper bound, a lower bound, or both, or none. Let's check. Let's start with upper bound. So 0.5, let me write it again, 0.67, 0.75, 0.8. If I claim that 2 over 3 is an upper bound, it will mean that 2 over 3 is bigger than every other term of the sequence, and that is false, since I have this bigger than this is bigger than this, and of course, every term to the right is bigger than 2 over 3. If I claim that 3 over 4, which is 0.75, is my upper bound, it will mean that 3 over 4, which is 0.75, is bigger than or equal to every term of the sequence, and that is not correct, since 0.8 is bigger than 0.75. If I pick 0.8 as an upper bound for my sequence, would that be correct? The answer is no, again, because I must have another term to the right of 0.8 that is bigger than, 0.8. Let us take the sixth term, for example, A6. So what will be A6? So A6 will be, when n is equal to 6, will be 6 over 7. And what is that in decimal? Let's check. So 6 over 7 is equal to 0.8571, and some few numbers following. So I cannot claim that 4 over 5 is an upper bound for this sequence, because I have a term A6. Even the fifth term is bigger than it, but the sixth term is obviously bigger. 0.8571 is bigger than 0.8. So can we now say that this sequence, with the way it's behaving, that this sequence is not bounded from above? It is bounded above. Let's be careful. If I claim that my upper bound is 1, the number 1, would that be correct? Let us see. You observe that as we keep going towards the right, of our sequence, the numbers begin to increase indefinitely, and they keep going very, very close to 1. But these numbers never get to 1. They become as close to 1 as possible. Let us see. Let us check what the 1000 term of the sequence will be. That would be 1000 over 1001. If you punch out, you see that the 1000 term of the sequence will be 0.99. Where am I? 1000 times 0.99 9000999. What do you see? The 1000th term of the sequence still doesn't exceed 1, but it is as close to 1 as possible. 0.9999000 is very, very close to 1, but it doesn't exceed 1. Let us see what happens if we take the 1,000,000th term of the sequence. That will be 1000006 zeros over 1000005 zeros and 1. You divide this. You check again that this number will be very close to 1, but it will never be 1, and it will never be 1 and beyond 1. So if I claim that 1 is an upper bound for my sequence, it will make sense, because 1 will be bigger than every other term of the sequence. If you put n as 100 billion, 100 billion over 100 billion and 1 will not exceed 1. So 1 qualifies to be called an upper bound for the sequence because 1 is greater than all the elements of the sequence. Now, if you recall from the definition, we have never said that the upper bound must be an element of the sequence. No. Hence the strict inequality in this case. Because in the previous cases, our lower and upper bounds were members of the set, or were elements, or were terms of our sequence. But in this case, 1 is an upper bound, and 1 is not an element or a member of the sequence, or a term of the sequence. But 1 fulfills the property that it is greater than all the elements of the sequence, or all the terms of the sequence, I beg your pardon. So 1 is an upper bound for the sequence. Question is there, or can there be any other 1 is an upper bound for the sequence? Not the upper bound, is a upper bound, a upper bound. Because there are many more upper bounds. If I pick 2, will 2 be an upper bound? Yes, it is. Because 2 is bigger than every term of the sequence. Can 10 be an upper bound? Yes. 10 is bigger than all the terms of the sequence. So the very first upper bound that I see there, which is very clear, is 1. 1 is bigger than all the terms of my sequence. The other upper bounds include 2, 10, 1.5, 1.8, 1.6. What every other real number that is bigger than or equal to 1 is an upper bound. So all the real numbers, say R, that are bigger than or equal to 1 are upper bounds. Clear? Good. Is this sequence bounded from below? Let us check. What we are asking is there a number in this sequence, or is there a real number that is less than or equal to all the terms of our sequence? Let us look at the values one after another. If I claim that 2 over 3 is the lower bound of my sequence, which is 0.67, what I am saying is that 0.67 is smaller than every other term of my sequence, and that is not correct, because 0.67 is not smaller than 0.5. So 2 over 3 cannot be my lower bound. If I say that 1 over 2 is my lower bound, what I am saying is that 1 over 2, which is 0.5, is smaller than or equal to every other term of my sequence. That makes sense because none of these terms exceed 1, which makes 1 the upper bound. But none of this term is less than 0.5. As a matter of fact, 0.5 is less than every other term of a sequence. And of course, 0.5, which is half, let me use half, 1 over 2, is less than all the terms of the sequence. And of course, 1 over 2 is equal to itself. So 1 over 2 is less than or equal to all the terms of my sequence. That qualifies 1 over 2 to be called a lower bound. So the lower bound, one of the lower bounds, a lower bound of the sequence, one of them, the first one I see is 1 over 2. Like we've learned already, that 1 over 2 is a lower bound for my sequence does not mean that 1 over 2 is the only lower bound for my sequence. There are infinitely many more lower bounds, because every real number to the left of 1 over 2 that is bigger than 1 over 2 is also a lower bound. For example, to the left of 1 over 2, we have a number here, say 1 over 3, which is 0.3. 0.3 is clearly less than 0.5. So 0.3, which is 1 over 3, is also a lower bound for my sequence. 0.2 is a lower bound for the sequence. 0.1 is a lower bound. So every other real number that is smaller than or equal to 0.5 is also a lower bound for my sequence. So this sequence is a beautiful sequence because it is bounded above by 1, is bounded below by what? 1 over 2. Beautiful. Since the sequence is bounded above by 1 and bounded below by 1 over 2, it is now safe to say that our sequence is a bounded sequence. So the sequence n over n plus 1 with the terms half, 2/3, 3/4, 4 over 5, and so on is a bounded sequence. Since the sequence has an upper bound as well as what? A lower bound. So how do you write it? We write an is bounded above by what? By 1. So that means an is less than, and since 1 is not a member, or 1 is not one of the terms of our sequence, so it will be strict. So an is less than, strictly less than what? 1. And since an, the sequence is bounded below by half, and half is a member of this sequence, so we say less than or equal to half. So this simply means that the sequence an is bounded below by half, the sequence an is bounded above by 1. So why is this inequality not less than or equal to? Let me say it again. It is not less than or equal to because this real number 1 that bounds this sequence from above is not a member of the sequence. It's not in the sequence. The terms of the sequence get arbitrarily close to 1, but they never get to 1. So 1 is not a member of the sequence, but 1 borders the sequence, to the right. So 1 is an upper bound because it is bigger than every term of the sequence. Half is a lower bound because this half is smaller than or equal to every other term of that sequence. The inequality at the lower bound is less than or equal to because 1 over 2 is a member or a term in a sequence. We can write this in another form that is shorter. Since the sequence an is bounded and is bounded above by 1, we can just write that an is bounded by 1. So when we see this in mathematics, this simply means that the sequence an is bounded. So this carries all the information you find here. This tells us rather that this sequence has an upper bound as well as a lower bound. I hope that is clear. So the sequence, in conclusion, the sequence an equal to n over n plus 1 into from n from 1 to infinity is a bounded sequence. It's bounded below by half and it's bounded above by 1. So you see that this issue of boundedness it's a very trickish issue. We have to be very careful, else we just misfire. Unbounded sequences. A sequence an where n goes from 1 to infinity is said to be unbounded if it is not bounded. That is, it's not bounded above and below. We have already seen examples where a sequence had an upper bound and we said that the sequence was bounded above. Where it had a lower bound without upper bound, we said it's bounded below. So if the sequence has an upper bound, we say it's bounded above, but we cannot say it's bounded. So for the sequence to be bounded, it has to be bounded above and below. So if the sequence has an upper bound without a lower bound, the sequence is not bounded. When the sequence has a lower bound and no upper bound, the sequence is also not bounded. If the sequence has no upper bound and no lower bound, the sequence is also not bounded. So we'll say that the sequence is unbounded. Therefore, for a sequence to be bounded, the sequence must have an upper bound as well as a lower bound. Now let us take an example of a sequence that is clearly unbounded. It has no lower bound and no upper bound. Let's look at the sequence minus 1 raised to the power n times n. Let's get a few terms of this sequence. When n is equal to 1, we have minus 1 raised to the power 1 times 1. That is minus 1. So the first term there is negative 1. When n is equal to 2, we have minus 1 raised to the power 2 times 2. That is 2. We have here 2. When n is 3, we have negative 1 raised to the power 3 times 3. That is negative 3. When n is equal to 4, we have minus 1 to the 4th times 4, which is 4. Let us take two more terms. When n is 5, we get minus 1 to the 5th times 5 minus 5. And when n is 6, we have minus 1 to the 6th times 6, that is 6. Of course, there are infinitely many more terms of this sequence. So we want to investigate the boundedness of the sequence or otherwise. So we shall start with the upper bound and then the lower bound and then conclude if the sequence is bounded or unbounded. So as usual, let's place our terms on our number line: plus infinity, minus infinity. So the first term there is negative 1. Negative 1 is somewhere here. So that's the first term. Second term is 2. 2 is to the right of negative 1. 2 is somewhere here. The third term is negative 3. And of course, negative 3 is smaller than negative 1. I've explained already that 3 is bigger than 1. So negative 3 is less than negative 1. So negative 3 will be to the left of minus 1. So minus 3 is somewhere here. Next term is 4. 4 is to the right of 2. Next term is minus 5. Minus 5 is to the right, left of minus 3. We have 6. And it goes on and on. So this is our first term. Let's call it A1. Second term, A2. Our third term, A3. Our fourth term, A4. Yes. Our fifth term, A5. And the sixth term is what? A6. I see this sequence is jumping. First term is here, second term jumps over, third term jumps this other way, fourth term jumps over. So we call this, an alternating sequence. The figures are alternating. Minus plus keeps jumping from one place to the other. So even at that, we can still discuss the issue of, boundedness here. Let's start with the upper bound. If I claim that 2 is an upper bound for this sequence, it will mean that 2 is bigger than every other number in the sequence. Let us see. 2 is bigger than minus 1. Of course, 2 will be bigger than all other negative terms on the left. That is correct. But 2 is not bigger than 4. So 2 cannot be an upper bound. 4 can also not be an upper bound for the same reason, because 4 is not bigger than 6. 6 also cannot be an upper bound because there will be an 8th term here, A8. If you follow the sequence, A8, which will be 8, and 8 will be bigger than 6. 8 also cannot be the upper bound for the sequence because there's an A10, there's a 10th term that is bigger than 8. there will be a 12th term bigger than the 10th term. There will be a 14th term, to the right, bigger than a 10th term. There will be a 16th term. So that property will continue. So there is no single, real number that we can pin out, that we can just take out and say, okay, this number is bigger than every other term of the sequence. So this sequence here is clearly not bounded above. Not bounded above. Clear? There is no real number to the right that is bigger than every number or every term of the sequence. Whatever real number you pick, there will always be another real number after it that is bigger than all the terms of the sequence. Let's talk about the lower bound. If I claim that -1 is my lower bound, that would mean that -1 is smaller than every other term of the sequence. -1 is smaller than 2, 4, 6, and 8, and of course to the right. But -1 is bigger than -3. So -1 cannot be the lower bound. -3 also cannot be, because -3 is bigger than -5. -5 cannot be, because -5 will be bigger than the next term, which will be -7. -7 cannot be, because it will be bigger than -9. And this will continue indefinitely. So there is no single real number to the left that I can say that is smaller than every other real number on every other term of the sequence. Clearly also, this sequence is not bounded below. So this is a clear case of unboundedness. The system doesn't have an upper bound and it has no lower bound. Hence, the sequence -1 to the n times n is unbounded. Clear? Take note, if it is bounded above and not below, it's unbounded. If it's bounded below and not above, it's unbounded. If it's unbounded below and not bounded above, it's also unbounded. So the sequence is only bounded when it is bounded above and bounded below. Least upper bound or supremum. A sequence that is bounded above has a least upper bound, which we also call the supremum. The supremum, denoted by SUP of AN, or the sequence, sup AN. So a sequence that is bounded above has a least upper bound or the supremum. And we denote the supremum or least upper bound as SUP, least upper bound or LUB. Let me explain this. Let us go back to example 1. We had a sequence -1, -n squared, n from 1 to infinity, and we had the terms -1, -4, and all that. We had, agreed and investigated that this sequence was bounded above by what? By -1. Now, we had said then that -1 is not the only upper bound of the sequence. That -1 is one of the upper bounds. So -1 is a upper bound, 0 is another upper bound, 1 is an upper bound, 2 is an upper bound, 3, and there's so many of them that are upper bounds. Of all the upper bounds of this sequence, xn. So we have the sequence here, xn. And one of the upper bounds is -1. Of all the upper bounds of the sequence, the smallest, the least of them all is what we refer to as the supremum of the sequence, or the least upper bound of the sequence, LUB of xn. So the first upper bound we see here is -1. The second one is 0. We have many other upper bounds. Okay. Now, every other upper bound that lies to the right of the first upper bound are clearly bigger than -1. So, of all the upper bounds of this sequence, -1 must be the least. Since -1 is the least of all the upper bounds of the sequence, we now say the supremum of the sequence xn is what? -1. So, while -1 is a upper bound, -1 is the supremum. Because there can be many upper bounds, but there can be only one supremum. So -1 is a upper bound, 2 is the upper bound, but -1 is the supremum or the least upper bound. What are we saying here? That we could have so many upper bounds for a particular set or a particular sequence, but the least of all the upper bounds is what we call the least upper bound of the sequence or the supremum of the sequence. In example 3, we had something similar. For the sequence n over n plus 1, n from 1 to infinity, with the following terms. We had agreed here that all the terms of this sequence, no matter how large n is, will get arbitrarily close to 1, but they will never get to 1. And so 1 was a upper bound. So we said that 1 is a upper bound. We also established that there are several other upper bounds, So, for example, 2 is an upper bound, 10 is the upper bound, 1.5 is the upper bound, 1.6, 1.8, 1.2.7, 10.1, they are all upper bounds. There are too many of them. Of all these upper bounds, 1 is the first and 1 is the least of them all. So since 1 is a list of all the upper bounds, it means that the supremum of our sequence n over n plus 1 is equal to what? 1. Or the least upper bound of the sequence is 1. What does this mean? That of all the upper bounds, this guy here is the smallest. So we call it the least upper bound. So the concept of supremum only comes in when the sequence is bounded above. So a sequence that is not bounded above cannot have a supremum. And once a sequence is bounded above, there is bound to be a supremum. Are we there? Very good. Greatest lower bound or infimum. A sequence that is bounded below has the greatest lower bound or infimum, denoted by INF of xn. So we explain with an example. Back to example 2, where we had the sequence 2 raised to the power n, n from 1 to infinity. This sequence we had agreed that 2 was a lower bound for the sequence, since 2 was less than or equal to all the terms of the sequence. I also explained that there are several other lower bounds apart from 2. For example, 1 is a lower bound, 0 is a lower bound, all the negative integers are lower bounds. In fact, all the negative real numbers are lower bounds, and so on and so forth. So of all these, lower bounds, which of them is the biggest or the greatest? Now, it must be 2, because 2 is bigger than 1, 2 is bigger than 0, 2 is bigger than every other number between 1 and 2. 2 is bigger than them. So, since 2 is the greatest of all the lower bounds, we'll now say that the infimum of the sequence 2 raised to the power n is equal to what? 2. Infimum or greatest lower bound, GLB, 2 raised to the power n, is equal to 2. What are we saying? That of all the lower bounds of the sequence, which are infinitely many, the one that is of interest to us is the infimum. And what's the infimum? The greatest of all the lower bounds. And here it is 2. In example 3 again, our sequence n over n plus 1 was bounded below by half. And because it was bounded below by half, there were several other lower bounds. So 1 over 3 is a lower bound, and there are so many of them to the left. Of all these lower bounds, which of them is the greatest? It must be 1 over 2. So since 1 over 2 is the greatest of all the lower bounds, we now say that the infimum of the sequence n over n plus 1, 1 to infinity, is what? Is half, 1 over 2. That is the infimum. We call it infimum, or we call it the greatest lower bound, equal to 1 over 2. Now, this number 3 example again is a case where our sequence has both infimum and supremum. Recall, for this set, that the supremum of this set was 1, and the infimum of the set is now what? Half. So while some sequences have, supremums without infimums, which will imply that they have upper bounds and no lower bounds, is it not so? Others will have infimum and no supremum, which implies that they are bounded below and not bounded above. Others will have both infimum and supremum, which tells us that such sequences have upper bounds as well as what? Lower bounds. Hence, they are bounded sequences. Like this example, it's a bounded sequence. It has a supremum, it has an infimum, as well as what? A supremum. Some sequences have no infimum and no supremum. Like in our last example, the sequence minus 1 to the n times n was unbounded because it had no lower bound, it had no upper bound. Since there was no lower bound, there cannot be an infimum. And since there was no upper bound, there also cannot be a supremum. So the issues of supremum and infimum can only come in where there is either a lower bound, that there will be infimum, or an upper bound. And of course, where there's an upper bound, we can talk of what? A supremum. So in our next lecture, we shall be looking at the limit of a sequence. Till then, please take care of yourself and bye-bye.